So in the introduction, I'd like to tell you why we will go for this kind of econometric analysis. What is the purpose of econometric analysis? For this, the main reference is Stock and Watson. Already you have the book with you. Now to begin with, if I like to give some definition of econometrics, so at the broad level, econometrics is a science and art of using economic theory and statistical techniques to analyze the economic data. So I hope you are familiar with this kind of definition. We have some model in our background, which we are getting from the economic theory, and we are trying to assess whether this theory is right or whether we need some kind of editing of this theory, etc. Looking at the real life data. So econometrics is a science and art, you can say, by which we can assess the economic theory using the statistical techniques, and this helps us immensely to develop the empirical branch of the subject. Now, what is the relevance of this thing? First of all, now if you consider any example, okay, so consider this example. Does reducing size of the class improve elementary school education? Suppose this is the question, and everybody has some idea, if the size of the class is small, in that case, the faculty will be able to give attention to each and every student, and the level of education will be better. Always we feel that, not at the school level only, for each and every level we feel that kind of thing. However, there was one classic test considering 420 California school districts in 1999. In Stock and Watson, you will get that thing. So they did this kind of experiment, and they found that if they control by other factors, that is the income of the household of those school students, and if they control parental education, etc., they are finding that the students who are there in the schools where the size of the class is lesser, they are doing better just because of the fact that they are coming from wealthier section of the society. The household income of those students that is higher compared to the students, those who are going to the schools, public schools. Okay, so the smaller numbers they got in the private schools, and they are finding that those parents could arrange for some other additional classes, some other complementary courses, etc. And for that matter, actually the performance of the students are better. So it is not the size of the class, but something else which result in better results of the students who are going to the schools where the size of the class is smaller. So if we control for several factors, in that case, the situation may become different. So many a times our idea about the economic theory may not be true. If there are controlling matters, in that case, we may get different results, or we will get the logic why they are doing better, whether because of the size of the class or because of something else. So econometric tools will help you to consider this kind of controlling factors and really find out what is the reason of these particular result, why we are getting this particular outcome, which economic theory fails to assess, or economic theory fails to give any proper direction regarding this kind of questions. Okay, next. There is another example. Is there racial discrimination in the market for home loans? Okay, so this kind of question comes many a times. There are different social groups or socioeconomic groups, and many a times we find that the availability of credit of several groups are lesser than availability of credit of other groups. This is a very common picture. Okay. Now, there is another very important study, and that study found that only 28% of socially unprivileged applicants were denied mortgages. Actually, while only 9% of the other privileged applicants are denied. But this is for the matter of fact that the total application of unprivileged group that was lesser compared to the privileged group. And number two, there were a lot of um, a lot of problems in the forms submitted by this group. Okay, because of their education level maybe, or because of their level of understanding maybe. So there were some problems in their applications. Okay, so bias is not there with respect to the race. Problem is in some different place. So problem may be there because of lesser education. Problem may be there because of lesser level of understanding. However, problem is not there because of the color of the skin. Okay. So before concluding there is bias in mortgage market, these data must be examined more closely to see if there is a difference in probability of being denied for otherwise identical applications. So there is some problem in the application process, and for that matter, their loans were denied. So econometrics helps us to understand this kind of problems also. Okay, so what kind of policy we will take, whether we will add more efficiency to the form filling, or whether we will go for more efficiency in the process of giving credit. Okay, so here we are finding that we need to focus on filling of the forms, not on on the basic issue of whether their mortgage will be denied by the credit market, etc. So econometrics helps us, and before coming to the conclusion there is a bias, econometrics helps us to find out the real position and frame the policy accordingly. So first advantage is controlling for other factors and then assessing. The second advantage is, before coming to the conclusion that there is a bias in the system, it will help us to truly assess the system, and thereby the direction of the policy may go towards proper channel. The third problem in context of economic theory is simultaneous causality. Under many circumstances, in context of economic variables, you will find that if you define one variable as y, that is the dependent variable, and another variable as independent variable, always there is a confusion where whether y determines x or x determines y. This we call the problem of simultaneous causality. I'm not understanding whether happiness results in more efficient production mechanism and resulting in growth of the economy, or more efficient economy results in happiness. That we don't understand. Happiness is result of economic growth, or economic growth is result of happiness. There is a big question. Okay, so this kind of issue appears many a times in context of economics. We don't understand whether this will be the dependent variable or this will be the independent variable. Actually, there is the issue of endogeneity. So econometrics helps us to sort out this kind of endogeneity and conclude the things in a better way. So that is the third advantage of learning this kind of courses. Fourth important thing is forecasts, and in this COVID time, continuously there is forecast. You are getting all these ideas, So looking at history, looking at the present context, what will be the future? That is the important role of learning economics. So what will be the future, what we will get in the future, what will be the future policy direction, that again and again we need to decide. Okay, so as applied economics, you will be able to do that if you learn the subject very well. Good forecast, perfect forecast. Okay, so this is the fourth thing which we will emphasize in this course. Then one particular question. So far, I talked about the advantages of learning econometrics, or why we should go for this kind of applied courses. Okay, the next thing I want to tell you, many a times we feel that the econometric model building exercise develops the causal relation. That is, y is cause of several things. Okay, or if x is a particular cause, y is effect of that. Generally we look at the thing in this way. So the relationship between y and x is a causal relationship. Okay, now the relationship between y and x will be a causal relation if and only if x, no way is related to y. X is truly external. If x is truly external, in that case, we can say that yes, y is the effect of x, or x is the cause of y. Okay. However, in social science, there will, most of the times, there will be some kind of relation between y and x. Okay. We cannot say that y is totally independent of x and then x is trying to find out or explain the variation in y. So if x is not totally external to y, in that case, we cannot say x and y are causally related. Now, to understand the things better, so please go through this slide. All the issues mentioned earlier concern causal relationships among variables. In common usage, an action is said to cause an outcome if the outcome is the direct result or consequence of that action. For example, touching a hot stove causes you to get burned. Drinking water causes you to be less thirsty. Putting air in your tires causes them to inflate. Putting fertilizers on your potato plants causes them to produce more potatoes. Causality means that a specific action leads to a specific measurable consequence. Okay, so please focus on the last line. Causality means that a specific action leads to a specific measurable consequence. However, in social science, you will find that under most of the circumstances, a specific action may not result in specific measurable consequence, and therefore, the relation is not always causal. Okay. In case of randomized controlled experiment, you are going for this kind of causal relationship. However, in econometrics, always you will not get causality. Okay. Now, coming to causation via regression, as I mentioned, for a causal analysis, we need the independent variables are truly exogenous. If the independent variables are truly exogenous, in that case, really you will get a causal relationship. Otherwise, you will not get causal relationship between y and x. So please keep this point in your mind. Your regression doesn't mean always you are considering a causal relationship. Now, keeping all these points in your mind, why we are going for this kind of course and what is the meaning of regression. Sometimes it is a causal relation. However, many a times it is not at all a causal relation. Next, what we do, we start doing the model building exercises in context of econometrics. So generally we start with a two variable kind of thing, linear regression with one regressor. We start with this kind of thing. Okay, so suppose we try to understand this kind of questions. A state implements tough, tough new penalties, on drunk drivers. What is the effect on highway fatalities in that case? Or a school committee cuts the size of its elementary school classes. What is the effect on its student standardized test scores? So these kind of questions we like to address using a two variable case. However, you are understanding, if we consider this kind of simple models, there is no chance that we will be able to control for other variables. So if you look at the second issue, a school committee cuts the size of its elementary school classes. What is the effect of its students' standardized test scores? If you consider these relationship only, you are trying to avoid the control mechanism, okay? Where you can introduce the wealth holding of the household, you can introduce the parents' education, you can introduce, gender of the student, etc. So it's really a simple structure. If you consider only the simple structure, basically you are losing the essence of learning this kind of courses. So in this semester, we will consider extended framework. We will consider a number of explanatory variables in our model. And again, we will look at the assumptions, estimation, and hypothesis testing. Any questions so far?
Ma'am,
Yes.
ma'am, in the second question, you told that we have to consider the gender of the student, but why we will do so? How is the gender is related with the test scores?
We are considering the controlling factor, gender may or may not be related, so many a times we consider this kind of thing, especially for the higher education. We consider the fact that boys will go for more technical education, girls will go for more arts related education, humanity related education.
Why
Okay,
is
so
it?
this is the, it's not why is it, generally these are the research hypotheses, okay? If there is any gender bias in choosing the stream, that is a research question. Why it is, uh, you know um, if you consider the gendered economy, if you consider that kind of thing, education related papers, you will find that many a times we consider this kind of thing, okay? So
So,
whether the proportion of girls is lesser in higher education or proportion of girls is higher in education, so what will be the policy direction for including more girls in the education system? All these things are there, in your country, in fact in your state. If you look at several policies like Kanyasri, or if you look at central government's Beti Bachao policies, the question is why these policies are there, because of addressing these issues, isn't it?
yes, ma'am. Got it.
Okay.
Ma'am,
Yes.
ma'am, you told that a causal effect means the direct consequence of a specific action. If
Yeah.
that consequence is not direct, that it is indirect, then we do
Mhm.
not call it a causal effect or a causal relation.
Yeah, yeah, that's true. In regression analysis, we know, you have to look at the factor really whether X is exogenous or not. In your regression analysis, maybe you are addressing the causal relation, but there is a confusion, all regression is giving us the causal relationship. It's not so. Sometimes it is just taking the association on. Okay.
Okay, okay,
Sometimes it
ma'am.
is checking the causal relation, and sometimes it is checking association among the variables. There is no causal relation in this. We are checking causal relation between y and x variables.
Ma'am, can you explain with an example?
Okay, so look at this slide. Um, if we go through this slide, for nearly a century, investigators in social sciences have used regression models to deduce cause and effect relationships from patterns of association. There is some pattern, positive relation between y and x, or negative relation between y and x, and that was treated as causality. Always they treated regression as the causality. Okay, so in their version, regression is an estimation of conditional expectation of y given x, that is average value of y for given value of x. Now, for a causal analysis, we need the independent variables are truly exogenous. Okay, now truly exogenous means, we will be not able to accommodate this kind of relationship. Okay, now if you look at this kind of relationship, growth and happiness, you don't know actually whether happiness results in growth or growth results in happiness. You can keep growth in your y variable and happiness in as x variable. Happier the people, they will work more, or they will work more efficiently, and that may result in better production. Or alternatively, this also may happen, you know people are happy because the economy is growing, isn't it?
Yes, ma'am. Yes,
So
ma'am. Now I
here,
get it.
yeah, happiness is not external. You know, if you consider, forget about happiness. If you consider investment income relationship at macro level, okay, whether greater investment results in greater income or greater income results in greater investment, there is a confusion.
Yes, ma'am. This is
Is a
exactly.
function of I, or I is a function of Y, there is a confusion. Okay,
Yes,
so
ma'am.
if you look at a number of economic variables, always you will face this kind of confusion. So whether you will keep these variable as your in place
Basically,
dependent
you want to
variable.
basically you want to say that it when it is difficult to identify which is the dependent variable, then
Hmm.
we would say that we have no causal effect,
Truly
causal.
external, yes. If X is truly external, in that case, regression is equivalent to a causal relationship. But if it is not truly external, in that case, we are if there is simultaneous causality. How we will say that this is the
Yes,
effect, this is the cause.
yes, ma'am. Thank you, ma'am.
Okay. Anything else?
And basically, in simultaneous causality, x and y variables affecting each other.
Y and X. Yes, X affects Y and affected by Y. Endogeneity means this kind of problem. The variable X explains Y and is explained by Y. Okay, this is the
Okay.
concept. Okay, this is the standard definition of endogeneity. Okay, so go through all these slides, go through all these ideas and check Stock and Watson for this part. So I hope the things will be clear to all of you. So it's a complex world. Social science is not that easy. It's not a lab based science that you are putting the things in a particular ratio and that will result in a particular thing. In physical sciences, we get the things in that way. However, when you are looking at the social science, you are looking at the society, economics, politics, you will not get this kind of cause and effect relationship. Most of the times you will find that x's are not truly external to the system. Okay, so with this background, now I'll shift to the k variable analysis. Two variable you will revise, Now, while I'm talking about k variables, a number of questions, proofs, as well as numerical exercises of two variable analysis will be there as a part of k variable analysis. So it will be your task to revise all the assumptions, estimation, and hypothesis part of the two variable analysis. While I'll discuss the numerical exercises in context of k variables, sometimes I'll consider one explanatory variable and we'll discuss a few numerical exercises. Okay. However, you need to revise the entire two variable analysis you learned at your undergrad course. So directly I'm moving to a k variable classical linear regression model. Okay, so do anyone have idea why we call the model classical model, or the idea of classical model is based on what? Why we call a model a classical model? Or what are the properties of classical model?
Ma'am, full employment.
I'm talking about econometric model. I'm not talking about macro models.
There are five basic assumptions for which a linear model is called a classical regression model.
What are those five assumptions?
The disturbance term is normally distributed. The expected value of the disturbance term is 0. There is heteroskedasticity, there is autocorrelation, and x and ui are not related.
Okay, so Rudra, there are some mistakes, there will be no heteroskedasticity, homoscedasticity.
Oh
There
yes,
will be no
homoscedasticity.
autocorrelation, isn't it? So
Yeah, no autocorrelation and homoscedasticity.
yeah, so expectation of error is equal to 0, as you mentioned. Variance is a constant which we call homoscedasticity. There will be no autocorrelation, that is, all the errors will be not interrelated. And you mentioned about the normal distribution of the error term. What else?
And the explanatory variable and the disturbance terms are linearly independent.
Yeah, xi's and ui's are independent to each other. Okay, very good. So if this kind of context is there, so if what I wanted to, the answer I wanted from you is like that: if the random error in a regression model follows a particular set of assumptions, then we call a model a classical model. And those specific assumptions are the assumptions, which Rudra has just discussed, told us. So our classical linear regression model will be based on these assumptions. But since we are extending the number of explanatory variables, we have to add a few assumptions, and everything we will discuss in terms of matrices and vectors. That will be the only difference. So I'll add one or two more assumption in it, and I'll discuss the entire thing in terms of the matrices and vectors. However, the idea will remain same as he discussed. Okay, so regression analysis is concerned with describing and evaluating the relationship between a given variable. Often we call that variable a dependent variable, and one or more other variables, often called the explanatory or independent variables. And we denote the explanatory variables or independent variables by the set of variables x1, x2 to xk. So on one hand, we have the independent variable, set of independent variables, and here we are considering we have k number of independent variables, x1, x2 to xk. And in the left hand side, we have the dependent variable, which we also call the study variable. Okay. So study variable or dependent variable is there, and the set of explanatory variables, and sometimes we'll call it the control variables also. Control variables or explanatory variables will be there in the right hand side. You may know the entire idea of regression was introduced by Sir Francis Galton from England who was studying the relationship between height of children and height of parents, whether there is any kind of relationship between the two. Okay. There are several objectives in studying the relationship between the study variable and explanatory or the control variables. Analyze the effects of policies that involve changing in individual X variable. For example, if we change the expenditure on education, or if we change in expenditure on health, whether that will result in greater output in the economy, or if we make some certain kind of changes in the trade policies, whether the export-import ratio will change or not. So this kind of thing. Analyze the effects of policies that involve changing the individual X. So in X, we are considering this kind of expenditure or trade policy, etc. Examine whether any X variable have a significant effect on Y. Okay. And forecasting. So these are the three main things. What will be the direction of the policy, whether changing X we will be able to change Y or not, and whether the analysis between Y and X will help us to forecast the matter. Now, to study the subject, we first start with the exact relationship. Economics gives us the exact relationship. If we think about the basics of microeconomics, the demand and supply equation, the equations are given by Q is equal to A minus BP, or QS is equal to A plus BP, that kind of relationship. These relationships are exact relationships, exact functional relationship. It's a deterministic mathematical relationship. Okay. Now, while we are going for the statistical analysis, or while we are going to check this kind of theory on the basis of the data, we are collecting data from reality. So what we are finding that for a given X, we can find out only the expected value of Y. Okay. So a statistical relationship which does not give unique value of Y for a given values of X, but can be described exactly in probabilistic terms. We cannot say quantity demanded for oranges is equal to A minus BP. Okay. However, given the prices of oranges, we can expect this can be the demand. So we can calculate only the expected value of Y, not the true value of Y. Okay. So to clarify the idea, we can start with the exact relationship, exact linear relationship Y is equal to alpha plus beta X. When we are going to the reality, we do not know whether we will get these or not on the basis of the data. So we will, statistical things or econometric things tells us we should add one random error to the structure. Okay. So if I look at the observed value of Y, if we replace Y by Yi and X by Xi, the relationship can be presented as Yi is equal to alpha plus beta Xi plus Ui, because the data gives you expected value of Y for given value of X only. So we need to randomize the model, adding one random term. In terms of scatter diagram, if we try to understand the thing, when you are trying to find out, the relationship between quantity supplied and price, say, you are getting certain points, you are not getting exact line fit. Okay. So you can think about a fit throughout those points. However, you are not getting the fit looking at the data. You are getting the scatter only. Okay. And if you look at the scatters and if you consider the exact fit through that scatter, you will find that some of the points are lying on the fit, whereas some points are above it, some points are below it, some points are to the right, some points are to the left. Okay, so all these things will happen. And all these discrepancies of the dots or the scatters from the exact fit is called the random error. So when we are going to the reality, we have to rewrite the model as yi is equal to alpha plus beta xi plus ui. Okay, now the question is why all the scatters do not lie on the fit, why we get this kind of problem. So there are several reasons why an error or disturbance exists, why the scatters are not always on the fit, though the theory is telling us this will be the fit. Okay, so the problem may be omission of explanatory variables. While we are presenting the demand equation, maybe we are considering price of the commodity, price of the substitutes, price of the complementary, income of the consumer, and we are moving up to taste and preference. Because of some problems in collection of data or some issues in the reality, suppose we are not including the geographical region, somebody is including geographical region, then maybe the person is not including the demographic condition of the country. So there are so many things there. So omission of several explanatory variables may result in this kind of differences, or may create a distance between the point and the line. Okay, next, aggregation of few variables in a single variable. On each and every variable, we may not collect the data. It is not possible to collect the data. So, we may go for a kind of aggregation, model misspecification. Y does not depends on, there is no instantaneous relationship between yi and xi. Rather, there is a relationship between yi and xi minus 1. So somehow we are considering this kind of misspecification, and that results in this kind of random error. There may be functional misspecification as well. As I mentioned earlier, actually what may happen that x cube is affecting yi, however, I am considering xi. So functional misspecification may result in this kind of presence of random error. And finally, measurement error. Okay, the scales or the unit of measurement we are using in measuring yi and all xi variables, that may result in some kind of incorrectness in the system, and therefore we will find that errors exist. Okay, and if you look at the entire construct of the social science, you will find that these are the things which will happen always, and therefore we will always find that the relation is not exactly y is equal to alpha plus beta x. Rather, the relation is yi is equal to alpha plus beta xi plus ui. Now, in a k variable construct, we will expand this idea introducing k minus 1 number of explanatory variables. So I'm writing the model as yi is equal to beta 1 plus beta 2 x2i plus beta 3 x3i plus beta 4 x4i, and moving up to beta k xki plus ui for all I is equal to 1 to n. Okay, to give the idea of k variable model, therefore, we are considering k minus 1 number of explanatory variables, and there is one dependent variable. So therefore, it is a k variable linear model. Now, this model is basically this one. y1 is equal to beta 1 plus beta 2 x21. x2 is the name of variable, and this 1, 2 to n is basically observation on variable x2. x2 is the first explanatory variable. To keep parity with beta 2, I'm naming the variable x2, and this x2 variable, for x2 variable, I'm considering the n number of observations. Okay. So y1 is equal to beta 1 plus beta 2 x21 plus beta 3 x31 plus up to beta k xk1 plus u1. This is for the first observation. Now the second equation is for the second observation. y2 is equal to same intercept beta 1 plus beta 2 x22 plus beta 3 x32 plus up to beta k xk2 plus u2. And we can go on like this up to yn. So yn is equal to beta 1 plus beta 2 x2n plus beta 3 x3n plus up to beta k xkn plus un. So if we look at the structure, or if we look at this complete extension, we are finding that in the left-hand side, we have a vector. We have y vector of order n by 1. There will be n number of rows and single column. So yi is basically yi vector having n rows in it and a single column. So it's y vector. And then we can write the entire X matrix as the first column is 1, 1, 1, 1 up to n number of 1. The second column is x2, 1, x2, 2 up to x2n. Third column x3, 1, x3, 2, x3n. And it will be continued up to xk1, xk2, xkn. And that will be multiplied with a beta vector. Because if you look at the coefficients of all the equations, coefficient values remain same. So there is a common beta vector which has been multiplied with the set of explanatory variables. Okay. And finally, there is u vector, vector for the random error, and this is similar to y vector. Okay, y1, y2 to yn. U1, U2 to UN. Okay, the structure of this random vector of the random error is identically equal to the structure of the vector for the dependent variable. So if I use matrix algebra, look at the structure and tell me whether this thing is understandable or not. There is y1, y2 to yn. Please add here, or please note down, this is a vector of order n by 1. Okay, so add n cross 1 here. This is a vector of order n by 1. Okay, and then we are writing the X matrix in this format. The first column is 1, the second column is for the variable x2, and we are considering all n observations. Then there will be column for x3, all n observations, and finally we will move to the variable xk, and we will have all n observations there. That will be multiplied with the beta vector beta 1, beta 2 to beta k. Now, if you consider the matrix multiplication here, if you multiply the first row with the first column, the matrix multiplication will go like this. You will get beta 1 plus beta 2 x21 plus up to beta k xk1. Okay, so you are getting back your first equation. And check what will be the order of the matrix X. Anyone?
Kn.
I didn't get it. What will be the order of matrix X? Yes, somebody tried to tell me, please.
Ma'am, Kn.
Kn. What is the
K by
number?
n.
What is the number of rows here? What is the number of rows here?
K plus 1.
Number of rows is k plus 1. I'm finding that number of rows is simply n is the number of rows because we have n observations. So, we have n rows here and we have k number of columns. This is the first column consisting the values of 1, and this is the second column, and we are moving up to kth column. Okay, so this is a matrix of order n by k. Everyone, look at the matrix. Isn't it a matrix of order n by k?
Yes, ma'am.
Everybody is understanding that it is a matrix of order n by k?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. And this is a beta vector, and order of this vector is k by 1. Everybody is getting that?
Yes, ma'am.
So please note down, order of beta vector is k by 1. plus this is the error vector. Just like y vector, it is of order n by 1. It is of order n by 1. N is the number of observations and k is the number of unknown parameters. We have beta 1, beta 2 up to beta k. So k is the number of unknown parameters. So if we simplify the model, we can write it in this format y is equal to x beta plus u, where y is a vector, x is a matrix, beta is a vector, and u is also a vector. Okay, so if I specify the orders, etc., so if you please look at this structure, it is this structure. Y is equal to x beta plus u. So please note down y is of order n by 1. So it's a vector. Then equal to x matrix. X is of order n by k. Then we have the beta vector. Beta is of order k by 1. And we have the u vector as well, which is given by u n by 1. Okay, so why we are presenting this kind of k variable regression model, yi is equal to beta 1 plus beta 2 x2i plus beta 3 x3i plus up to beta k xki plus ui. In that case, what population equation we have in our mind? It is given by this one. The expected value of y given x1i has a specific value x1, x2i has a specific value x2i, and so on up to xki, xki is equal to xk, sorry, x1i is equal to x1, x2i is equal to x2, xki is equal to xk. Given this particular set of x, what will be the expected value of y? So the population equation, is given by this beta naught plus beta 1 x1 plus beta 2 x2 plus up to beta k xk. And on the basis of the sample observations in terms of the scattered diagram, etc., we are presenting the same model as yi is equal to beta 1 plus beta 2 x2i plus beta 3 x3i plus beta k xki plus ui. Okay. Do anyone have any question regarding the modeling part? Any problem regarding understanding the vector and matrices in the model building part?
No, ma'am.
So next we consider the assumptions of the model. And as Rudra mentioned, it's a classical model, so there will be a specific framework. So now we will go for a specific framework and you will find that all the assumptions or most of the assumptions concentrate around or center around the random error UI. So the difference between the economic model and the econometric model centers around the random error UI. So how we can specify it, what will be its quality, what will be its characteristics, that we discuss. Now, while we discuss characteristics of any statistical variable, we start with the central tendency. We talk about central tendency, then we talk about dispersion, etc. So here also we will do the same thing. So when we are trying to form some idea about the random error term, we are starting with the properties of the random error terms. So first we are mentioning something regarding the central tendency, expectation of UI. Okay, so the first assumption is zero mean. Expectation of u vector. This u is nothing but u vector, the vector u of order n by 1. We are considering this to be a null vector. So expectation of u vector is a null vector, which we can also present as expectation of ui, I for all I is equal to 1 to 2n, is equal to 0, 0, 0, 0, etc. So expectation of ui is equal to 0 for all I is equal to 1, 2 to n. Now, what is the implication of this assumption? So while we are drawing any fit and we are considering corresponding scatters, some of the scatters are coming above the line, some of the scatters are below the line, and if we drop perpendicular from the points above the line, if we drop perpendicular from points below the line, we will find that number of perpendiculars are more or less same. The number of positive discrepancies are more or less same to the number of negative discrepancies. Okay. And for that matter, it is only a consistency requirement. We are assuming expectation of u vector is equal to 0 vector. However, it's not a very stringent assumption. It is only a consistency requirement, since the volume of positive discrepancies may be equal to the volume of negative discrepancies. Okay. So remember this term. This is a consistency requirement. So this is not at all a stringent assumption. The next we consider the spherical variance covariance matrix. Please concentrate on the presentation for this part. Now, when we go for the two variable analysis, separately we talk about variance of ui and covariance of ui uj. And we introduce the notion of homoscedasticity as well as non-autocorrelation. However, when we are considering u vector, actually, when we are trying to define variance of u vector, we are getting the entire variance covariance matrix. And this variance covariance matrix is a square symmetric matrix. Therefore, we call it a spherical variance covariance matrix. So value is basically var covar matrix. So how we are defining value? It is expectation of u minus expectation of u multiplied with u minus expectation of u transpose. Okay. So we are considering the square of the things in terms of matrix algebra. In case of variance, we consider the square of the things. So we need to consider expectation of u minus expectation of u, that should be multiplied with u minus expectation of u transpose. This is the formula for variance. Now, if we look at this formula, so just a minute. Please look at this tape, variance of u vector, that is expectation of u minus expectation of u curl, u vector, multiplied with u vector minus expectation of u vector. Now, all this expectation of u vector, this expectation of u vector, that is equal to null vector, which we got from the earlier assumption. So we can eliminate this expectation of u, and simply we will get expectation of u prime. Now you think about your u. U is a column vector, and that is multiplied with a row vector. So please write down the order of u. U is of order n by 1, and we are multiplying it by one vector which is of order 1 by n. So what will be the order of u transpose? U is of order n by 1 and u transpose is of order 1 by n. So what will be the order of u transpose?
N by N.
N by n? Okay. So the order of the variance covariance matrix of the error is given by n by n. So are you understanding? It will be a squared symmetric matrix. multiplying two vectors, however, you are getting a squared symmetric matrix. Are you convinced?
Yes, ma'am.
Everybody?
Yes, ma'am.
Okay, so once we consider expectation of u prime, this is equivalent to expectation of u1 square, u1, u2 up to u1 un, then u1 u2, u2 square up to u2 un, u1 un up to un square. Okay, just a minute. So I hope everybody is getting that. Expectation we are considering when we are multiplying the column vector with the row vector, we are getting the values u1 square, u1, u2 up to u1, un, and then the second row will come like this, and finally the last row will come like this. Any question for this kind of specification of u prime matrix? Any question, any query? Is it okay?
Yes, ma'am.
Okay, so if this is fine, now we will operate expectation on each of the terms in the matrix. So it will be expectation of u1 square, expectation of u1, u2, and it will move up to expectation of u1, un, and similarly for the second row, expectation of u1, u2, expectation of u2 square, up to expectation of u2, un. Finally, for the last row, we will consider expectation for all the variables. So if we do so, operate expectation on each of the terms in presence of homoscedasticity, all these expectations, expectation of u1 square, expectation of u2 square, up to expectation of un square, that will be same, and that is given by a constant, say sigma u square. And all off-diagonal terms, that is expectation of ui uj's, expectation of u1 u2 up to expectation of u1 un, then in the second row expectation of u1 u2 up to expectation of u2 un, finally for the last row expectation of u1 un up to the term before this, all these values will be exactly equal to 0. In other words, we will get this kind of structure, we will get this kind of structure here. This kind of structure. In the diagonal, we will get, while we will take expectation, we will get sigma square. And in off diagonal, we will get all zero values. Okay. Now, this can be presented by sigma square in. So, if you take sigma square common from this matrix, we are getting the values 1 along the diagonal, and all of diagonal terms are equal to 0. So, we are getting sigma square in. Is it clear to all of you? How we are getting sigma square in?
Ma'am, can you please repeat? Hello?
Yes.
Ma'am, can you please repeat homoscedasticity and non-autocorrelation? I didn't get that.
Okay, so are you understanding expectation up to this? Expectation of this we are getting if we multiply the column vector with the
We
row
are
vector.
generating expectation to each and every term.
Okay. So now you have to take expectation on each and every term. You need to operate expectation on each and every term. So you are getting expectation of u1 square, expectation of u1, u2 up to expectation of u1, un. Similarly, that thing will be done for the second, third, fourth row, and finally for the nth row. Now, here we assume all expectation of the square terms which are there in the diagonal are constant, and the value is given by sigma u square.
Yes, ma'am.
Okay, we are assuming all these expectations in the diagonal are constant, and the value is given by sigma u square.
Yes, ma'am.
We further assume that expectation of all ui uj's, that is equal to 0, and by that matter, all of diagonal terms are equal to 0. Okay.
Yes, ma'am.
So we are getting this is equivalent to sigma u square in.
Yes, ma'am. We will get an identity matrix.
Yeah. So this actually a set of double assumptions. Assumption of homoscedasticity and assumption of non-autocorrelation. By assumption of homoscedasticity, we are setting all expectation of ui square to be equal to sigma u square, constant. And by the assumption of non-autocorrelation, we are considering all expected values of cross products of error terms that is equal to 0.
Yes, ma'am. Now I got that. Yes, ma'am. Thank you, ma'am.
Okay, so maybe you know all these things. However, to understand the difference between homoscedasticity and heteroskedasticity, here we have a line fit, actually we have scatters around the line fit, and we may consider this kind of distributions of the scatter at each and every point. Basically, there are distributions. However, we are considering the distribution as x is equal to 15, x is equal to 20, x is equal to 25 at 3 values. So here we are getting the dispersion of the scatter around the fit, around the exact relationship beta naught plus beta 1x that is fixed. The dispersion is fixed, So this is the idea of homoscedasticity. The distribution or the dispersion of the scatter around the fitted line that is fixed. However, if we look at this diagram, we are getting this dispersion is changing as we are moving from the value 15 to 20 to 25. We are finding that for different strata, the distribution is different. The distribution is different. So this is the idea of heteroskedasticity, spread of the scatters around the fit that will vary in context of heteroskedasticity. However, that will be identical for homoscedasticity. Okay. For another example, this is the idea of homoscedasticity. Spread is same across different points of the line, and here the spread is changing. The spread is changing. We are getting different values of the spread or different types of spreads along the same line for different values, 8, 12, and 16. So this is the idea of heteroskedasticity when dispersion varies, and this is the idea of homoscedasticity when dispersion of the observation remains identical across the line or over the line for different values of x. So we have completed, basically 3 assumptions as we discuss in context of a 2-variable analysis. The expected value of error is 0. There is homoscedasticity, there is known autocorrelation. Next, we are going to the assumption of independence between x and u. Both x and u are there at the right-hand side of the model. In the left-hand side, we have y, the explained variable or the study variable, and in the right-hand side, we have x and u, the set of explanatory variables and the error term. We have those variables there. Okay. Now, here, to maintain the linearity of the structure, we need independence between xi and ui. The 2 terms are there, 2 varieties of terms are there, the set of explanatory or control variables and the random error. To maintain linearity of the structure, we need covariance between xi and ui should be equal to 0, or cov between x matrix and u vector, that should be equal to 0. Now, if we can ensure the qualitative difference between these 2 types of variables, then this condition is trivially satisfied. For example, error is always random. Now, if you can ensure x is non-stochastic, non-random, in that case, this covariance between x and u is equal to 0 will be trivially satisfied. There will be no problem in that. So non-stochasticity of x is a sufficient condition to have the independence between the x matrix and u vector. However, non-stochasticity of x is not at all a necessary condition to have this covariance equal to 0, because it may happen that x is stochastic, random, still covariance between these 2 terms is equal to 0, and we can perfectly maintain the linearity of the structure. Okay, so non-random x is a sufficient condition to ensure covariance between x and u is equal to 0. However, it is not a necessary condition. Now, in a k-variable analysis, to avoid any kind of noise in the system, we can assume that all the explanatory variables we are considering that will be non-stochastic in nature, so that this condition is trivially satisfied. Cov x u is equal to 0. So this is the first part of this assumption. Now I'm coming to some other issues here. The x we are considering here, that x will consist of all independent columns. Okay. Now, as long as we considered the 2-variable analysis, we had 1x and 1u in the right-hand side. Okay. When we are going for this kind of k-variable analysis, not only we have x and u, but also we have a number of x's. So if I say that linearity requires there should be independence between x and u, I also need to ensure there will be no linear dependence among all x variables too, isn't it? Are you understanding the logic? Are you understanding the logic?
Yes, ma'am.
Ma'am, what does non-linear independence mean?
Yes, I didn't get you. What is your question?
Non-linear independence.
Non-linear independence. Actually, when we talk about correlation, etc., we can talk only about the linear relationship.
No, ma'am, you told about non-linear.
No, I didn't tell anything about non-linearity. I'm telling that if I tell you to maintain the linearity of the structure, I need, the independence between x and u. Here, in case of k variable analysis, to maintain linearity of the structure, I also need independence between all x variables too. Are you getting my point, everyone?
Yes, ma'am.
Sraya, are you getting the point?
Yes, ma'am.
Joyon,
Yes, ma'am.
is it okay that not only the independence between x and u, you also need the independence between all x's? Okay. So these assumptions will be further add several issues as well, apart from mentioning that curve between x and u is equal to 0. We need to ensure, all x columns are independent to each other. This can be ensured if we consider rank of x matrix is equal to k. There are k number of columns here. The first column is 1, 1, 1, and second is starting from this value, and there is this column as the final column. So there are k number of columns here. Now, to indicate independence of these columns, we need that rank of x, row of x, rank of x should be equal to k. Rank of x should be equal to k. If rank of x is equal to k, that indicates all k columns are independent to each other. Now, before moving further, anyone, would you please tell me what is the meaning of rank condition of any matrix? Nothing related to econometrics in general. What is the meaning of rank condition? Anyone? Shubhangi?
Ma'am,
Yes.
to investigate two or more variables.
I'm asking for what is the meaning of rank condition? What is the meaning of rank in a matrix algebra? Any idea? Anyone? Upali or Ujan?
Um,
What is rank condition?
Ma'am, rank is the minimum of the number of rows and columns.
You know, uh,
Dimension of the vector space.
Upali is giving us the right direction. It is minimum of independent rows or columns. Okay, let me try to write this. It is minimum this is the rank condition. Okay, row is equal to row is the rank of a matrix indicates minimum of independent rows or columns. Okay, so if there are, say, we consider a square matrix of order 10 by 10. Now if I have 5 independent rows and 7 independent columns, in that case rank will be given by 5. Minimum of independent rows or columns. Independent means these rows cannot be generated from other rows. Independent column means these columns cannot be generated using other columns. So if I consider a 10 by 10 matrix and if I find that 5 rows are independent whereas 7 columns are independent, in that case the rank will be given by 5. Again, if we find that 3 columns are independent, whereas 2 rows are independent, 4 rows are independent, 3 columns are independent, 4 rows are independent, in that case, the minimum will be given by the number 3. So it will have the rank 3. Okay. Now, in a k-variable analysis, we want that, let me write, rank of X matrix should be equal to K. Rank of X matrix, that should be equal to K. That is the number of columns. K is the number of columns in an X matrix. Okay. So these has 2 indications. Number 1, all the K columns are independent because rank can be determined only by the independent columns. And it is also indicating another thing, K is less than N. K is less than equal to N. K is less than equal to N. 2 things it is indicating. If we assume that rank of X will be equal to K, to ensure all the columns of X matrix are independent and that we need to maintain linearity. First of all, we need independence between X and U, that we are ensuring considering non-stochastic X. First part. Second part, we want that all columns of X should be independent to each other. So the matrix X will have full column rank. Matrix X will have full column rank. Full column rank means the rank of X matrix is given by K. Full column rank means rank of X matrix will be given by K. All K columns are independent to each other. Third part, if I say K is the rank of X matrix, that indicates K is less than equal to number of rows, that is N. K is less than equal to number of rows, that is given by N. So are you understanding the logical development? First tell me that. Are you understanding the logical development?
Yes, ma'am.
Other students?
Yes, ma'am.
Okay, so here we are basically telling about 3 points coming to these particular assumption. I'm repeating, covariance between x and u is equal to 0 to maintain the linearity of the structure. And this we discussed in 2 variable case 2 at your undergraduate level. So you are familiar with this assumption. Generally, we consider non-stochastic x to ensure this condition. However, this is a sufficient condition. You should remember, not a necessary condition, because stochastic x can be also independent of stochastic u. In a k-variable analysis, to avoid any kind of noise in the system, we are considering non-stochastic x. And this non-stochastic x should be independent of the u vector. So we are ensuring that covariance xu is equal to 0. Now here we have a number of explanatory variables. So the second thing is we also need to ensure all x columns are independent to each other. Not only x is independent to u, but also columns of x matrix are independent to each other. In other words, x2i should be independent of x3i, should be independent of x4i, and xki should be independent of rest of the columns. So all columns will be independent to each other. Now this we can ensure if rank of X matrix is equal to K. What is the definition of rank? Minimum of independent row or columns. So in the rank condition, we are talking about independent rows or columns, and then we are considering minimum of the two. Now, if here we assume rank of X is equal to K, or X has a full column rank, then you are ensuring all the columns are independent to each other, because rank condition itself is telling us about independent rows or columns. So if I state rank of X is equal to K, this is stating the fact that all K columns are independent to each other. So are you understanding the second point now?
Yes, ma'am.
Okay. Finally, rank condition is not telling us about independence of rows and columns. It is also telling us rank should be minimum of independent rows or columns. So if I state rank of X is equal to K, that is indicating the fact that K is less than equal to N. Otherwise, how we will write rank of X is equal to K? So now we are coming to the third point. Rank of X is equal to K, and that K should be less than equal to N. If this step is clear, I'll go for the fourth step. I'll even specify the condition more, and I'll state that K is not less than equal to N, rather K is strictly less than N. Fourth argument, K is strictly less than N. Now, why we are considering K is less than N or strictly less than N? Rank condition is again satisfied if K is less than equal to N. However, we are going one step further and telling that here we will not consider K to be less than equal to N, rather we will consider K to be strictly less than N. For this fourth argument, we will introduce the idea of degrees of freedom. Degrees of freedom in a regression model, which is very, very important. Now, what is the degrees of freedom in a regression model? It is number of observations minus number of parameters to be estimated. In a k-variable regression model, n indicates number of rows.
Can you please repeat? Number of observation minus
What is n?
number of observation minus number of.
What is n? I'm asking you the question.
Ma'am, n is number of row.
And it is also the number of observations.
Yes, ma'am.
So number of observation is equivalent to number of rows.
Yes, ma'am.
And what is k?
Ma'am, k is number of column.
In a regression model, what k indicates? Number of unknown parameters of the model.
Ma'am, rank of x.
And it is also the number of, simply to understand the factor, to consider the basic regression model, k is nothing but number of unknown parameters we have in the model.
Yes, ma'am. Yes, ma'am. Yes, ma'am. Yes, ma'am.
So n minus k is nothing but number of observations minus number of parameters to be estimated. This
Yes, ma'am. Now I got that.
The difference between this number of observations minus number of parameters is called the degrees of freedom. Degrees of freedom in the analysis, degrees of freedom. This difference between n and k, that is the number of observations and number of parameters to be estimated, is called the degrees of freedom. Now, to understand the idea of degrees of freedom in a better way, let's go back to the regression model. N observation means we have n number of equations in the model. And we have k number of parameters in the model. If it is a standard mathematical analysis, then solvability of this model will depend on the fact that whether n is equal to k or not. Number of equations should be equal to number of parameters to be estimated. Number of parameters to be estimated here is given by k, beta 1, beta 2 up to beta k. Okay, so there are k number of parameters. So if n is equal to k, in a standard mathematical context, we will be able to estimate all these parameters. However, in a regression model, apart from estimating unknown parameters, you will find that in future, you need to estimate several other things as well. So your objective is not only to estimate all these unknown parameters, but also to estimate some other unknown components, like say population variance. Under most of the circumstances, you will have no idea about population variance and you need to estimate it. Already in a two-variable case, you got this thing. You don't know the value of sigma square, you estimate it. And you found that RSS by degrees of freedom, that is the estimate of sigma square. So estimation not only concentrates on these unknown parameters, but also it takes care of several other elements. So we need a gap between the number of equations and number of parameters to be estimated. Or we need a gap between the number of observations we have and number of parameters we need to estimate. This gap is called the degrees of freedom. In a regression analysis, we need a sufficient degrees of freedom in our hand. So to ensure the presence of sufficient degrees of freedom, we need that k should be strictly less than n. So 4 arguments at this point is cov xu is equal to 0. Second, rank of x is equal to k. Third, this k should be less than n. Fourth, thus we are ensuring linearity of the structure. We are ensuring the solvability of the parameters. And we are also ensuring feasibility condition. So let's try to understand these things in a better format. So the first argument, I hope you understood it because you did it in your last semester or at your undergraduate level too. Cov xu is equal to 0. The additional thing we are discussing here is, first of all, rank of x is equal to k. This rank of x is equal to k, this part. Okay, this part, this green box. This is our second argument to ensure linearity, to ensure independence among the columns of x. And this is called the solvability condition, because if the columns are not independent to each other, in that case, you will be not able to solve for the values of beta. Okay, so this we call the solvability condition. Further, we are adding one more dimension to it. We are telling that this k should be less than n. This k is less than n is called the feasibility condition, where n minus k is called the degrees of freedom. So all these issues are there in this particular assumption. And this we need to analyze, incorporate in a k variable case. In a 2 variable case, the structure was simple. So only ensuring the independence between x and u was sufficient. Okay. Whereas when we are going for a multiple regression, we need to ensure all these steps. Any question? Any question? Any question? Any clarification?
Ma'am,
Yes.
can you explain degrees of freedom once more, please?
Did you do econometrics at your undergraduate level?
No, ma'am, I do not have econometrics.
You didn't have econometrics at any course at undergraduate level?
No, ma'am.
Okay, so in that case, please go through the things properly because, you know, since you didn't have any econometrics course at undergraduate level, this course will be a bit heavy to you, you know, because it is the applied course.
Yes, ma'am.
For degrees of freedom, you know, as I mentioned, that is the gap between the number of observations and number of parameters to be estimated. Actually, in a regression analysis, apart from estimating unknown parameters of the model, we need to estimate several other things. There will be a series of several unknown parameters as well. So we need to have a degrees of freedom, you know, that is a difference between number of equation and number of parameters to be estimated, so that we can utilize all these degrees of freedom for calculation of other parameters. We don't have anything apart from the observations here. So we don't have anything apart from these equations only. So the equations are only raw materials in our hand using which we will develop concepts of all the things. So here we are finding that when we are going for modeling the society, the economy, apart from calculating the parameters, we have to calculate several other things as well. I hope you did inference at least.
Yes, ma'am.
Hypothesis testing,
Yes, ma'am.
used the chi-square, AFT, tau, this kind of distributions, and I hope then you got the notion of degrees of freedom.
Yeah, ma'am. I know this term degrees of freedom, but I do not know the exact definition of degrees of freedom.
Okay, so please check all these things. I
Okay, ma'am.
already sent you 2 books, so please check all these things. What is the meaning of degrees of freedom? In your
Okay.
statistic inference, you will find that if in a test for mu, when you have knowledge about sigma square, you have a particular type of degrees of freedom. However, if you do not have knowledge about sigma square and you need to replace sigma square by a square, you are losing 1 degree of freedom. Instead of n, you are using n minus 1. So we start the notion of degrees of freedom from that point. As we estimate one more unknown thing, we lose 1 degree of freedom. Okay, degrees of freedom is given by number of observations to begin with, and as we need unknown components in our analysis, we start losing degrees of freedom. In a regression model with k explanatory variables, you have to estimate all these k parameters, so the definition starts with n minus k. So n minus k should be sufficiently large to estimate any other unknown parameters in the system.
Okay, ma'am.
Any other question regarding the assumption? So if you go through all these things, you will get all these things are there. These ideas, the note on these, all these things are there. Now, so far, up to assumption number 3, we consider the assumptions which we need for estimation. For estimation, we do not need any assumption regarding the distribution of the error term. We need the assumption of distribution of the error term only for hypothesis testing. Okay, so all assumptions I discussed so far, this is more than sufficient if you want to estimate the unknown parameters. All these assumptions are fine, If you use these assumptions, you will be able to estimate the parameters. However, you will be not able to proceed for hypothesis testing. And for hypothesis testing, you need one additional assumption. That is the assumption of normality of error distribution. We are considering the fact that around the feed, there is scatter, or there are scatter points. And if I consider the distribution of the scatter points, these are all normal distributions, It has a mean mu, and the observations are distributed following the pattern of a normal distribution. Okay, so scatters are distributed normally like this. So any question, or you are understanding the matter? Here the mean values are beta naught plus beta 1x. If I consider any diagram, I cannot accommodate more than 2 points, Best of all, I can consider only a 3-dimensional space. So here along the x-axis, we are measuring x, and this is y, and along this axis we are indicating probability values of y. Okay, so here we are considering only one explanatory variable. So expected value of y given x, that is the fitted line, is nothing but beta naught plus beta 1x, that kind of fit, the exact relation. And scatters are distributed around this fit, and those distributions are all normal. The last assumption is large outliers are unlikely. So this is the only assumption where we are not talking about the random error ui. So this assumption is not related to the random error term. This is not the assumption for the random error part. It's a general assumption. Why we are going for this kind of general assumption? Because while we are talking about this kind of relationship or this kind of regression analysis, it is a mean-based approach. We are considering expected value of y given x, this kind of approach. Expectation of y given x. So it is a mean-based approach. And all of us have idea about the fact that if there are large outliers in the system, that is, if some x value is very, very dispersed compared to the rest, there is outlier in the system. In that case, mean will be affected a lot. Since the entire regression analysis is a mean-based approach, if I consider the presence of outliers, in that case, entire analysis will be affected. We will come to the erroneous conclusion. Hence, it is very important to assume large outliers are unlikely. In reality, what we do, once we get raw data, we clear the data first, and then later we consider the regression model, etc. So in the beginning, there will be a lot of tasks which will clear the data, will prepare your database. Okay, so you have to find out if there is any outlier. Using several tests, you have to eliminate those outliers, etc. Okay, so large outliers for the time being, since we will go for this kind of mean-centric approach, we are assuming that large outliers are unlikely, and these will be ensured if we can have expectation of xi to the power 4 lies between 0 and infinity, or expectation of yi to the power 4 also lies between 0 and infinity. Okay. Now this expectation of xi to the power 4 or yi to the power 4, that is the fourth moment, is related to the measure of kurtosis. Okay, so another way to ensure this condition is to assume that x and y have finite kurtosis. X and y have finite kurtosis. Okay, so we need to assume large outliers are unlikely, otherwise we will be not able to use the data for our regression analysis. This is ensured either by considering this condition, fourth moment of xi and yi, or if you consider the kurtosis value, look at the definition of kurtosis. Please check the definition of kurtosis. You did it in your undergraduate level. At any statistics book, you will get it. So look at the value of kurtosis and you will find that it is related to the fourth order moment. So you will understand the issue. Now, to have a pictorial presentation, this is an outlier. All x values are there, all observations are here, only this observation is here. Now, if you consider this observation too, in that case, you will get this kind of positively sloped line, OLS line, including outlier. However, if you eliminate this outlier, you are getting the relation is actually a bit negative. Okay, so this kind of mistake will take place. if we incorporate outliers in the analysis, the fit is negative, you are getting positive, etc. So to begin with, we assume that, the large outliers are unlikely. Any question? This completes the discussion of assumption of k-variable regression model. So far I discussed the model itself and the assumptions of the k-variable model. Any question, anything regarding this? And next we have to go for estimation. I think it will be better if I stop here today. So I'm closing the recording part. However,